Thank you for attending this talk. I know it can be hard. I'll try to keep it flowing and entertaining. So the title you see here is slightly different than the title that is out in front of the door. Same content, but I'll be talking about our efforts around supporting lower power large language models. One question: who here has heard of ChatGPT? One person? Everyone? Okay, very good. The generative AI hype is alive and kicking. From AI-generated code that could automate a lot of software development tasks to real synthesized drugs that are computationally designed by deep learning generative AI algorithms, to the ongoing writer's strike in Los Angeles, where workers are seeking protections against AI replacing their jobs. The future is either utopia or dystopia, depending on where you fall on this AI hype cycle. But in either case, it seems to be fueled by these large language models and, by association, the deep learning transformer. So the projected impact is deep and wide. Your kids might be doing their homework with ChatGPT, and if they aren't, they might be lying to you. The fintech version of ChatGPT might be as good of a financial advisor than a human. And the law version of ChatGPT apparently is passing a few state bar exams. The economic projections are equally as incredible. McKinsey predicts not only increased worker productivity, but incremental economic impact up to 70% in just a few years. So the downside of all this is the environmental impact. And that's exemplified pretty well in the table on the left. GPT-3, the precursor AI model to GPT-4, which is the subscription version of ChatGPT, to train that model from scratch takes 300,000 kilowatt hours of energy. And just to put that in perspective, the top 4 lines there, those represent 4 AI models. GPT-2, the precursor to GPT-3, 1.5 billion parameters. GPT-3 is about 180. BERT, 400 million, and ResNet 50, about 30 to 40. So these models continue to get bigger, and they're having this deleterious effect. In this case, energy efficiency is the issue. So what I would like to talk about, I'd like to level set first and give you guys a background in what this transformer, this AI model, is actually doing. If you don't know anything about it, we'll just do a quick little tutorial. I'll get into hardware. I'll talk a little bit about the traditional Von-Neumann architecture that we're all used to. I'll get into this new kind of processor where we interleave compute within SRAM and what kind of power that gives you. And I'll talk about the different ways that my company is using this design to customize that design for different kinds of AI workloads. We'll look at some metrics that are important to this community, token rate. And if you're interested, I'll give you some information on how you can try this all out. So at its core, these models, this transformer, this AI model, which is underpinning large language models, it's doing something very simple. All it's doing is next word prediction. So what does that mean? Given a token, oftentimes these things are generic to lots of kinds of data. In an NLP context, a token is just a word. Given a word, this algorithm just tries to predict the word that should follow it. Pretty simple. This idea dates all the way back to the 70s. In the 90s, the neural network community started to work on some interesting models to do this, recurrent neural networks, long short-term memories, exotic kinds of mechanisms like gated recurrent units. And they worked okay. They weren't like great, certainly not state-of-the-art compared to the models that were popular at the time, these bag of words models. Nothing really worked well until the transformer. So you might be thinking, well, couldn't a bunch of other words follow the word it? And you would be right. What these next token prediction models do is they're doing what you think they should do. They incorporate the context before the word, and that informs the predictive quality of the model. So when you are using the model for inference, you're using the context, that helps you predict the next word in the sequence. So the transformer is really good about tracking that context and updating it as it's processing the prompt. Another thing it does, the same word obviously can appear in different portions of the sequence, and so the transformer actually encodes that differently. And that makes sense, right? When a word appears in different parts of a sequence, it should have different semantic impact on a sentence. Transformer does that really well. And the pièce de résistance of the transformer is attention. And what it does is that different tokens within that sequence, different words within the context sequence, they can impart different predictive qualities to the current token prediction. And the transformer does a great job of doing this. It's called the attention mechanism. And so just to round out this little tutorial on the transformer, typically when we're training a large language model like a transformer, we're training it on a sequence which has a maximum size. These things started out with about 1K in sequence size. These days it's common to see 2K, 4K. Microsoft is pushing the max sequence size up to 50 and even over 100,000. So we're moving beyond sort of this simple chat context of just one question and one answer. Now prompts can be multiple sentences and a question. And the predictions can be multiple sentences. It can be chapters of books in some cases. So we typically talk about the context, the entire context window broken up into two phases. One is the prompt phase. That's typically human generated, especially in a chat context. And it could be a question. And then the model, once it gets the prompt and processes it, it goes into a completion phase where it predicts one token at a time. Often we call it autoregressive. So if we think about it from a technical and engineering perspective, we can process all of the tokens in the prompt phase at once. And that lends it a quality of being compute bound. We can throw more compute at the prompt to make that processing go faster. In the completion phase, we're limited by this autoregressive predict one token at a time. And at some point, you can't really throw more hardware at it, and it becomes I/O bound. And this will become important a little later. So this is a cute example, right? I chose a common, one of the most common phrases in English literature over the past, 100 years. But these days, right, ChatGPT and these large language models are taking more sophisticated input. So I figured, right, I'd ask ChatGPT, do transformers consume a lot of power? And to its credit, it confessed that yes, it does. And it gave me actually a litany of reasons why. And number 2 on its list was hardware. And so, kudos to ChatGPT for confessing some of the issues around these large language models. So if it's doing this simple thing with next word, next token prediction, let's look at a very specific kind of transformer, and let's look at the topology of what's going on. So the actual transformer, as some of you might know, was introduced in 2017 in the paper Attention is All You Need by Vaswani and a slew of other authors from Google Research who've now gone on to do some amazing things around neural networks. And it introduced the network that you see there on the left. And if you know anything about neural networks, for the most part, a lot of these layers you see there are pretty standard, right? Softmax layer, linear layer. It's got a residual connection and normalization. There's a feed forward block, right? These are pretty standard things if you've done neural networks for a while. The novelty is in the orange block that you see there, the attention block. And that's the mechanism that's doing the weighting of the context before the token you're trying to predict the next token on. Fast forward to 2023, we have all of these models, ChatGPT-4, Llama from Meta, Palm has Google has Palm, a slew of other startups that have slightly different topologies, but they're all transformer based. OpenAI is doing an incredible amount of revenue. They have a lot of infra costs, but they are posting a lot of revenue. And of course, NVIDIA is making record profits on its high margin GPU business. One thing I'll also mention is that the original transformer was intended to be for language translation tasks. So translating between a sentence in French to a sentence in German. It turns out you don't need that full model for this next token prediction. You just need that silo of neural network layers there on the right. And we call that the decoder side. The one on the left is the encoder side, but it turns out we just need the decoder side for next token prediction. The other thing I'll point out is if you noticed around that big block of neural network layers, that's called the decoder block. And you can actually replicate that many times horizontally in order to impart better predictive quality to your model. And oftentimes the AI researchers will talk about parameter scaling. The more parameters you add in very specific ways, the more of these emergent properties you're going to start to discover in these AI models. Also in that attention block, it says multi-head. You can actually partition that block horizontally into different heads. And that also scales the parameters of your model. So you can scale both vertically and horizontally to get more predictive power from these models. And that'll become very important a little later on. So let's look at a very specific one of these transformer architectures, ChatGPT-3. I mentioned it's the precursor to the subscription model of ChatGPT-4. And the large version of this model scales that decoder block 96 times vertically. And horizontally, it's scaled that attention block with 96 heads. So, right, if you start to sort of do all the math with all these layers, it's a tremendous number of parameters, 180 billion neural network parameters or weights. At the time, that was like super large. This work is a couple years old. Now we routinely see models up into the 500 million, and there's work even scaling that further. In terms of training this, I actually, in the previous slide where I talked about the energy impact of models, that example was that 300 kilowatt hour example training from scratch. This kind of training takes, tens of GPUs. It can take, many weeks depending on, right, how much hardware you throw at it. I believe that number comes from actually Google using their TPU pods, their versions of GPUs, for 4 days. That's where that number came from. So big models, consuming lots of power, issues with energy efficiency. I will make a note here, if this is something that you're interested in, each one of these layers in this neural network, in the transformer, does something very specific, and each one is very important. I'm not going to go through it here, but it's worth actually studying, taking a few hours and studying this. There's a lot of good material online, like the illustrated transformer, that can help you, right, understand why you need this kind of architecture. Okay, let me switch over to now hardware, now that we have some context of what these models are doing and why the parameter scaling is yielding these big models. So what I'm going to show you is a view of the chip of the Intel Meteor Lake die. And Intel is like the poster child for, I think, for the last few decades for the Von-Neumann kind of architecture. And if you don't know what that means, it's pretty straightforward. The idea is you have, a store of data, right? In one part of your architecture, your chip, you have your compute cores physically separated from the data. And you're just marshaling data back and forth between the data store and how it gets computed. And you might think that, right, that's going to have some impact on the latency of your computation and the energy efficiency, all that marshaling of data around. Let's look in particular on this chip. Let's zoom in here and look at where compute and where that data store is. So I'm showing you where the L1 cache is here. And where a couple of the compute cores are there. And so, in terms of the chip die distance, right, they're separated a good distance from each other. Is there a better way? So I'll be talking about the In-SRAM compute technology. It's all the way over there to the right. We call it the associative in-memory compute. And I'll talk about how we've dovetailed processing, a lot of processing throughout a fairly standard grid of SRAM. It's the golden age of hardware right now. And there are actually a lot of companies doing some interesting things in breaking the Von-Neumann design. I just bring up a couple of other companies I like here. Rain Neuromorphic. They're calling their design a digital in-memory computing. They're a startup. And I like these guys because they started designing their chip based on AI workloads, where a lot of us are sort of repurposing our technology and our new ideas to AI. They started out with AI. Mythic, they're an analog in-memory compute play. And if you guys have ever done anything with analog, it's tricky to get right in a semiconductor context, but they seem to be doing pretty well. They just got an injection of new funding, and they will be taping out both these companies will be taping out their chips, I believe, within the next 6 months or year. Let me talk about this In-SRAM compute. So I show you a picture of a PCI board, but what we're gonna do is focus in on the chip, the microprocessor there. What you're looking at there on the right is if you just ripped off the top of the chip and looked at it, it would look mostly like what you see there. That was the generation 1 of the chip. And I know some of you have seen microprocessors before, and I just showed you the Meteor Lake die, and you're like looking at that going, that doesn't really look as complicated as the Intel chip, and you would be right. And some of you might think that just looks like memory banks, and you would be right. And we'll get into why that is. If we just zoomed in on a certain section of this chip, what you're going to see is, for the most part, if you look at these yellow cells here, it's a standard grid of SRAM and the associated memory controller logic around it, word lines and bit lines. Right underneath, and here's the novel part, right underneath a small block of those SRAM cells is some compute logic, what we call a bit processor. So SRAM cells, right underneath is a bit processor. And these bit processors are fully programmable. And to give you a sense how close we are, why I say we dovetail bit processing throughout the SRAM, the average distance between the neighboring SRAM cells and that bit processor is 20 microns. So the distance is really, really small. If we just ignore the SRAM, the memory banks and the SRAM, and just look at the bit processors, what you'll find is that the bit processors actually connect to each other in this regular fashion. And we can start to think of these bit processors as a grid of compute in this chip. A bit processor, right, as you might imagine, given the size, is very simple. It's a bit processor. But it can mux in lots of different input. It can mux in the value of the SRAM cells that are right next to it, and it can also mux in the values of neighboring bit processors as well. So, right, you can start to think of this, as I said, right, this grid of bit processing. In the first generation of the chip, there were 2 million of these bit processors actually interleaved throughout 48 megabits of SRAM. And in addition, there is L1, but it's not like what we saw in the Intel Meteor Lake. We actually interleave L1 blocks throughout this chip as well. So we're interleaving these bit processors throughout the primary SRAM grid, and then L1 cache is also interleaved right throughout the chip. So, what does this mean for AI for these models? If we go back to the ChatGPT-3 example, right, we had this huge model with 180 billion parameters. It turns out for AI, and especially for deep learning, the predominant workhorse of computation for these models is going to be matrix multiplication. That's composed of max, multiply, and accumulate. And so if we think about this in a low power context, what does that mean? Are we actually running this 180 billion parameter model in a low power context on a PCIe board? No, actually. What we do and what we're looking into is more compact large language models, such as Meta's large language models, which are down to like 7 gigabytes with enough quantization. And we're repurposing our bit processor architecture in different ways and leveraging that IP to create custom designs for certain kinds of models. So I'll just talk about that here briefly. One of the designs we've been looking at is a more compact version of this, in which we're interleaving 32K instead of 2 million, 32,000 bit processors within 6 megabytes of L1. And this was working with a partner who wanted to use us for an IoT application, so 5 watts max. And we get some pretty good trillion operation Mac performance given this design. The interesting thing to note in this design, I was showing you the L1 and the interleaved bit processors. There is some SoC control logic. That's what you see there at the top. And we split the bank in half so that we can have some control path lines to all those bit processors. But what's interesting about the design, it's fairly simple and straightforward. And so it scales in easy ways to accommodate these different kinds of either die size budgets or power budgets. So that's what we're working with some of our hyperscaler partners on with respect to creating different kinds of designs, meeting certain performance benchmarks, but importantly, meeting these size, surface area, and power budgets. Right, it's very fungible. On the left, they wanted us to explore a 2.7 watt design for an IoT appliance, and we still get, and it scales pretty linearly. It's a very simple kind of architecture. And of course, for some devices, you can go up to 10 watts and still be kind of qualified as an IoT kind of device. The important thing to note about max and matrix multiplication is that a lot, these matrices are getting quite big, but you can do a lot of interesting tricks like, breaking down the large matrices into tiles. And then you're operating on the tiles and accumulating the values of the tiles in order to compose the results of the larger matrix. And those are the tricks we're playing with now to get those performance numbers. So, it's one thing to say TOPS and to say Mac performance, but it's another to actually measure and use metrics that are relevant for the application context. And we're talking about completion rate in large language models. So here are some benchmarks right off the presses. Again, we're using not using ChatGPT 4 or 3. We're doing a more compact model, Meta's Llama, and measuring our completion token rate. Remember, that was the IO bound part of this process, right? We had to predict tokens one at a time. And our early results are not bad, getting 42 tokens per second in some of our early experiments. This is parameterized by DRAM bandwidth. Like I said, the completion part tends to be IO bound, and you're going to be storing the weights and the context, right, in these IoT low power contexts in DRAM. And there's some extrapolation to future DRAM bandwidths, given HBMs and other kinds of ways to increase the power, or to increase the data bandwidth there. All right, so that's all I wanted to show you. If you want to try this out, we're working with a lot of AI researchers who are really interested in our chip for a lot of reasons. Not just the sort of this compute in memory design, but if you noticed in the design, there was no N/8, there was no FP8, there was no standard data type at all. And this is actually interesting to AI researchers because they're playing around with exotic kinds of data types, like micro exponents, where you have additional information about how to scale the exponent dynamically at runtime to play around with the dynamic range of various parts of the neural network. But it's given a lot of AI researchers some opportunity to play around with some ideas that weren't possible because they were constantly shoehorning, right, their ideas, right, into a standard microprocessor architecture. And this one is like, there really isn't, you're not locked into any kind of data format or even any kind of x86 assumptions about how you store and retrieve and store operands. And so we think it's an interesting design for researchers. We think it's a super interesting design for actually operationalizing large language models in a low power context, but also we're working on designs that are coupling a lot of these chips together in a data center context as well. So if you're interested in trying it out, we have a microcode compiler we're open sourcing. If you want to just try it to see if you can, get your head wrapped around this new non-Von-Neumann approach to microprocessor design. It's for C and Python right now. In the modular IP stuff, we're working with various partners, and we'll be presenting more at various conferences as we start to customize that in particular ways for particular kinds of AI workloads. But yeah, you can send an email to that address there if you're interested in learning more and playing with this chip. That's all I had. Yeah. So what I showed you there with the tops, that can be applied. That's matrix multiplication, so that can be applied to inference and for training, because matmul is the predominant computation in both training and inference. Like a lot of the new microprocessor designs, we're tackling inference first because in many ways it's easier to do. But we also have a play in training. We just haven't had time to get to it. So what I showed you here was just inference. I don't have a lot of time to get into some of the ideas we have around training too. But it's a very different kind of workload, training. Yeah, no, the training stuff, although it's interesting, there's been some interest in doing training at the edge, some kind of continual learning at the edge. I might actually steer one to use vector search at the edge for various reasons, just because, well, for a lot of reasons I won't get into. But I address the low power context here because that seems to be the topic of conversation is, right, these models are getting bigger. But we also have another effort to scale out the design in different ways and to stack these chips for a data center a machine. And that's more relevant for a training conversation, but I couldn't get it into this presentation deck. Yep. But it's general, as you see, right? It's a generic microprocessor architecture, and so it can be applicable for a lot of different kinds of workloads. And training is that's a natural extension of the stuff we've been doing with accelerating matrix multiplication. We just haven't gotten to it yet, but we think it's a good fit. Yes.
Eventually, there will be training done, broken down in a way that is, that, I'm looking at like $50,000 GPU that might be replaced by $50,000 GPU.
Yeah, I don't want to get too much into that because then I'm talking to you about like back of the envelope projections, and I like to sort of show, real numbers and real performance. But we think we have a good play there. And the power numbers look really good. At the end, right, and I think a lot of you have been involved in things where you kind of project calculations and right, you do numbers and adds and divides and stuff, and you get some great numbers, and then you start to actually integrate it with an application or a model. And your performance is like 60 or 70% versus what you thought it would be. And so we're kind of at that stage. It looks really good, but we want to start to prove it out first before we start to publicize what we can do in the training market. Sure. We really should show some, and we're working on it. They just weren't available for this presentation, but we're showing. It can be tricky, right? Because people do different things with models and claim that, I run ResNet 50, and you sort of dig in the numbers, and they've done all this quantization and stuff like that to fit their processor. And so it can get tricky to normalize that. Even if you go to MLPerf, right, you have to dig through, right, a lot of the details to see how they were able to get that performance number. And so we're in the midst of doing that kind of metric comparison. Yeah. Thank you. Yes.
So the process is very
You can think of it as a highly parallelized, Boolean logic compute grid. Yeah, you can program very simple Boolean kinds of operations. You have a lot of operands in which to feed the particular Boolean operations, but the NANDs and the XORs and the NORs of the world. Yes. Yeah, and we have support for, in the G2 version of the chip, we actually have support for 2-bit adding at near inside each of the bit logic cells. But you compose enough of those and you can get some pretty good performance around like Hamming distance, really large bit vectors and Hamming distance. There's Hamming distance seems easy until you have to count the results. And so we've added some 2-bit logic in that to increase that performance. But that add logic can be used for different kinds of workloads. And that's our G2 chip. Yes. Yeah. A lot of tricks we have. The technology we incorporate was, we acquired a company from Israel, Mikamonu, about 8 years ago. They had a lot of patents around how to do this efficiently. And we're working on more ways in which to efficiently route that data. But you bring up a good point. You do have to play some tricks with getting the data into the right place. Yeah. Thank you. Yeah, yes, and that's where the bit processors do their compute, is in the nearby SRAM cells that I showed, but also they use the L1. And L1, I always hate that we show L1 in any of these presentations because it's not like L1 in a typical microprocessor where it's like, it's this cache that software doesn't know about and is doing these secret things. You can actually, our instruction set lets you address that L1. In a lot of presentations, I'll call it local storage instead of L1 because I think L1 sort of, it connotes something very different. But our software instruction set lets you, move data between L1 and the bit processors and the nearby SRAM. Yeah. Yes. You should join my next presentation on training. As you know, right? It's a different kind of workload. It's different kind of patterns for accessing data and training, right? You have checkpoints, right? And you're storing your forward pass data, and so it's a different kind of workload. I have a whole new presentation I'm working on for training. Oh, in the future, yeah. But I want to actually get to the point where we're confident about I want to get to a point where we're not publicizing back of the envelope calculations and get it to a more real point before talking about it. But it looks very promising. Yeah. Sure. Yeah. So, I asked the same thing of our chip designer. He said, well, you should really be using sustainable, right, tops. And to address, you should be using sustainable, and I think he said overlapping I/O. So the power numbers and the MAC numbers you see there account for some level of what you're talking about, paging in that data while you're processing. It doesn't, that graphic is not great for that because, right, I was parameterizing different kinds of DRAM bandwidth, and that actually can affect the marshaling of the data from DRAM in particular ways. And it kind of complicated that graphic. But you're exactly right. Yeah, you do have to account for that. When we were working with the hyperscaler, they were just interested in our chip technology and what could we do for a sub 3 watt processor. They had their own sort of ideas about, and their own vendor for chiplet, for HBMs and chiplets. And so they sort of gave us those numbers. But you're right? When you're talking about a full solution, you need to account for that. But we were just charged with taking our design and finding the performance we can get at sub 3 watts. Yeah. And the other designs, I just wanted to sort of emphasize that, because it's such a simple kind of architecture, right? Just interleaving bit processors through SRAM and L1, it scales so easily. And so the IP is just very fungible when you're starting to customize a design for particular applications. But the idea was to take it, see what we could do under 3 watts. Yep. Yes?
You mentioned that you can mux in different neighbors.
Yes.
But how many inputs can you take and how many outputs do you have?
Yeah. Yeah, so the one I showed there was, let me give you some specifics on this one, I believe. So this was our G1 design, and that bit processor actually there's a bit processor for 24 SRAM cells that are right above it. And so each of those SRAM cells can be one of the operands for one of the Boolean operations you can program. And then also we have north, south, east, west for the neighboring bit processors. And those can actually also be operands into the bit logic. There are some rules about which ones, some complicated rules about which ones you can use at what time because of the way it's laid out, which got improved in G2. But in general, you have those, that muxing data available to you. And then you can store the result back into an SRAM cell. And that can also feed a neighboring bit processor. Yep. All right, thank you very much. Thanks for staying.